Okay, so now we're gonna discuss about the notion of local compactness. So the definition of locally compact is that, well, given a space, it is locally compact at a point x if we have that there exists a compact subspace of x such that it contains a neighborhood of x. So we say the space is locally compact if the above holds for any x and x. And observe that if the space x itself is compact, then it is automatically locally compact because it would just pick c equals to x, right? X contains, of course, contains a neighborhood of x, which is again the big X itself. So, yeah. Examples: R is locally compact, right? Because if we pick any point, right, x, we can find a and b and some neighborhood, right? Compact. And we have Q, give it as a subspace topology inherited by R. This topology, it is not locally compact. So R is locally compact, but the rationals is not locally compact. Let's verify this fact. Well, this fact is not an easy fact, so let's just verify it. Now, so suppose we have this, something like this, where U is neighborhood and K is compact, and is a subset of rationals, where U is open-ended rationals and K is a compact subspace of rationals. Then U contains some basis element, right? Some neighborhood of X. And neighborhood is in form of A, B intersect with Q. Well, inside A, B, we can fix a C that is irrational, and we find a rational sequence that converges to the C. Well, from here we can see that, well, for any first we define any subset of rationals, we define a limit point, A prime as the limit point of A and Q. Okay, so the irrational C is in this prime, right? Because for any neighborhood C of Q, right, C must be in something like this, right? And we let V be the intersection of AB and ST and intersect Q. This is a neighborhood of C and Q, right? Because for any neighborhood of C, right, we intersect with AB. And this, right, is a subset of AB intersect Q, which we can, of course, find in Rn, such that is a rational and is in V, right? It's in V and is in ST and it's in Q. This is a neighborhood of C, so by the convergence, right? So what we have, also K is a compact subspace of a Hausdorff space Q, right? So K must be closed, which means that this prime is contained in K prime and K prime is contained in K, because K is a closed subset of Q. So the limit point of K and Q, right? Limit point K and Q is contained in K, which means that C is in K. But C is irrational, K is a subset of the rationals, which is clearly a contradiction, right? So we have shown that if we have something like this, then we get a contradiction, right? We get a contradiction from here. Okay, so now comes the big theorem of locally compact Hausdorff spaces. So this gives a rise to the notion of compactification of a topological space. So the theorem states that given a space X and X is locally compact Hausdorff, if and only if there exists a topological space Y such that the topology on X is equal to the topology, the subset topology of X inherited from Y. And also Y subtracted by X is a single point, so Y has only single point more than X. And this point Y itself is a compact Hausdorff space. And furthermore, we have if Y and Y prime are two spaces satisfying 1 to 3, right? So if Y and Y prime both satisfies this, then there's a homeomorphism between Y and Y prime, such that on X is identity map. Because, well, this is clear enough to show, right? Because they both have a single extra point more than x, right? So if y has the extra point p and y prime has the extra point q, we can just establish a homeomorphism that is identity on x and takes p to q, right? And in fact, this is our idea, but we're going to show something that is more general. So in part of uniqueness, we prove something in more general cases that if x1 and x2 are homeomorphic, both locally compact Hausdorff, then if y1 is the space satisfying that for x1 and blah, the extra point is p, and y2 is the space blah, blah, blah for x2, and y2 minus x2 is equal to q, then we have y1 and y2 are homeomorphic. So this is our special case, right? When x1 is equal to x2, right? So we showed this, and the uniqueness follows by our general case. So first, let's establish a homeomorphism from x1 to x2, say as f. Now we extend f prime, extend the function such that on x1 is equal to f, and f prime p equals to f, p is equal to q. And we're going to check that this is a homeomorphism. Well, by symmetry, right, if we have a bijective continuous function, it is, well, I mean, if we have a bijection, right, we can just show that it is an open map, right? We show f prime is the open map. Then the inverse is also an open map, right? So then we'll show that f prime is a homeomorphism. So it suffices to show that f prime is an open map. Now, we're going to show this, okay? So for u open in y1, we want to show that f of u is open in y2. For this u open in y1, if p is not in u, okay, if p is not in u, then f prime u is equal to fu, right? And fu is open in x2, right? Because f is a homeomorphism, and u is open in y1, right? Then u intersects x is again equal to u, right? And u intersect x is open x1 and x1. So this is equal to u, so u is open in x1, right? So f of u is open in x2 because u is open in x1 because f is a homeomorphism. Okay. And, well, because y is T2, right, this Hausdorff is T2, y2 is T2, then is the T1. T1 means that single points are closed. Singleton sets are closed. So y2 minus x2 are closed, which means that x2 is open in y2, right? Which means that f prime u is open in y2 for any u open in y1. Okay, now what if p is in q? If p is in q, well, we're going to check it because, okay, let's just consider why we delete the u, right? It is then closed in y1, okay? And it is a compact subspace of y1, right? Because y1 is compact, right? y1 is compact. And c is contained in x1, so it is also a compact subspace of x1, right? And we have this. Okay, from here, because the FC is also compact, right? Subspace of x2, because f is continuous. And x2 is a subspace of y2, so FC is a compact subspace of y2. And y2 is T2, right? So compact subspace of Hausdorff space are closed. So f prime c is closed in y2. And now, back to u, right? C is equal to y1 subtract by u. And then we have this equality. And this is closed on y2, so f prime u is open on y2, so we're done. And this is the verification of this equality. So take a look at it and verify it by yourself. Okay, to save some time, because otherwise we're gonna verify the logics over and over again, and instead you might not get what we're doing. So our main goal right now is to prove the theorem, to prove that there exists to prove our theorem first. Okay, so this is the proof of uniqueness. So the uniqueness is done. Now, we're gonna show our main goal here. Our attention should be here. Okay, so suppose that X is locally compact Hausdorff, we can take an object that is not in X. Well, this is by Zermelo-Fraenkel set theory that, well, the detail is, okay, it's beyond the scope. But anyways, by ZFC, we can choose an object that is not in X. Okay, and we adjoin it, we call this new space Y. Now we're gonna topologize Y, we're gonna give it a topology. So we just give what the open sets looks like in Y. It consists of two types of open sets. The first type is that you're open in X. And the second type is Y subtract by C, where C is a compact subspace of X. So these are the two classes of open sets on T. And of course, we have to check that this is indeed a topology. Okay, so all below is going to check that this is indeed a topology. So empty set is type 1, right? And empty set is closed, and the compact X, right, is closed and compact X. So the empty set is compact subspace of X, right? So Y is also in the topology, right? This is some logic, like this is something indirect showing that Y is open. Okay, so empty set on Y is in T, and we're gonna check intersections, finite intersections, and this is of type 1, and this is of type 2, right? And you just have to, you're supposed to be able to figure it out by yourself. It's just set theory at this point. It's nothing topology here, because yeah, exactly. I mean, finite union of compact space is still compact. That is no doubt, and yeah. And from this equality here, X minus C1. Well, C1 is a compact subspace of what? Of X, right? X is Hausdorff, so it is closed. So C is closed in X, so this is open in X, and this is also open in X, so this is of type 1, right? Open set in X. Okay, and we're gonna check unions. Arbitrary union of open sets in X, well, of course, this is still an open set in X. And unions of those type of sets by De Morgan's law, right? Because, well, so each C beta is closed, right? Because like from here, right? I mean, C beta, I mean, okay, it's self-closed because it's a compact subspace of T2 space X, so it's closed. So the arbitrary intersection is closed, right? But the intersection C, this C is a subset of some beta node compact. So C is of course also a compact subset of beta node, which is a compact subspace of X. Okay, so Y minus C is of type 2. And the mixture unions. Well, this is gonna be equal to, this is U union, this is Y minus C, and this is really equal to Y minus C minus U, and this is the verification of here. Okay, it is really long. It's like doing the logic homework, right? It's really long here. I mean, here are the answers, right? So in fact, we have this equality, and it's a type 2 because C minus U is X minus U intersect with C, right? You're not in U, right? But you're in C, right? So it's this intersection here, and this is closed in C, right? This is closed in X, right? So this is closed in C, right? Which is compact set. C is a subspace, blah blah blah. I mean that application we've worked in multiple times already. Okay, so now we're gonna show that X is a subspace of Y, and the purpose is for this to show that if T is a topology on X and T prime is a subspace topology on X, we want to show that these two topologies are the same. Okay, so for this direction, we have this. It's really easy. And for this direction, we have, again, right? It's really easy, not really deep. And we also have to show that Y is compact. Okay, to show that Y is compact, for any open cover of Y, right, the collection A, then A must have type 2, right? Say Y subtracted by C, because we remember the extra point here, right? None of the open set in C that contains this. So if it's an open cover, it must contain at least one set that it looks like Y minus C. And for the other collections, I mean for other sets that is in the collection that is not equal to Y minus C, we can, for those, we get a new collection A prime. So for each of those, we intersect with X. Right, I think there's something wrong here. It should be all the S lambda is at X with S lambda not equal to Y minus C. Yes, this is right. Okay, so for those, it is a covering of C, right? Because this covers Y, and ignore Y minus C, right? This covers C. It's a covering of C with open sets in X. Oh, if it's a covering of open sets in X, right? Since X is compact, we have finite of them, right? And finite of them adjoined with Y minus C is really a finite collection that covers Y, which shows that Y is compact. Okay, and Y is also Hausdorff. For any X not equal to Y, we just discuss by cases. If they're both in X, then we're done, and because X is Hausdorff, and if one of them is the new point, we finally gonna use the local compactness, because X is locally compact, right? Then X is in U, that is contained in C. Then we have this, right? X is in U, and this is in Y minus C. So we have this joint union of neighborhoods of X and infinity. Okay, so this is the implication. Now for the converse. The converse is suppose that Y is a space as like 1 to 3, then X is a subspace of Y, which means that X is also Hausdorff because Y is Hausdorff. And to show that for any X is locally compact in X, we have to show this, right? It's locally compact. We want to show that it's locally compact Hausdorff. Okay, to show that it is locally compact, first we pick disjoint neighborhood of X and the extra point. Then for this V, Y minus V is a closed subspace of Y, which is compact. Okay? And it is compact subspace of X. Okay? U and V are disjoint, which means that U is contained in Y minus V, right? And X is in U, right? X is in U, and Y minus V is compact subspace of X. So this is what we have now. We have a compact subspace of X such that it contains a neighborhood of X. We just use the extra point compactness. And this is really it, the big theorem. Okay, so the proof is really long, and during the proof you might forget what we're supposed to be doing. So just to remind you, this is our theorem. Locally compact Hausdorff is equivalent to the exists in bigger space such that it contains X as a subspace, and that is compact Hausdorff, and it only has one extra point. Okay, and it's unique in the sense of up to a homeomorphism. Okay, now with the same X and same Y as above, so don't forget about them, just with the same X and same Y as above, if X is not compact, right, then for the point that is y minus x, it is a limit point of x. Why? Because any neighborhood of P must look like y minus c, but x is not compact, right? If x is not compact, then c must be a proper subset of x, right? Y equals t, it must be a subset of x, but it can't equal to x because we assume x not compact, so this is a proper subset of x, which means that y minus c and x is not empty, right? This implies this, but this is equal to this, x minus c. X minus c is not empty, right? Because it's a proper subset, right? X minus c is not empty, which means that any neighborhood of P intersects x, right? Intersects x. So the closure of x is equal to y. Okay, so from here, what we can see is that we can give a definition on this. So given y a compact Hausdorff space and x is a proper subspace of y such that the closure of x is equal to y. So motivated by above, then we call y is a compactification of x. And if y minus x is a single point, we call this a one-point compactification of x. And from above, we show that x has a one-point compactification if and only if x is locally compact Hausdorff and is not compact. Okay, it has a one-point compactification. And here's a remark. From the proof of uniqueness, we see that the one-point compactification of x is unique up to a homeomorphism. Given x locally compact Hausdorff that is not compact, and if y prime both one-point compactification of x, then we have they both satisfy 1 to 3, so they're homeomorphic. Okay, exactly. This is the proof, right? If y prime both, then it must satisfy at least 1 to 3, which means that they are homeomorphic. And again, right, if they're homeomorphic, then their one-point compactification are homeomorphic, right? Non-compact. Okay, so this is just a bunch of definitions. And here's an example that is interesting that I want to write it down. I just wrote it down. So so first consider the mapping that takes pi over 2 to 5 pi over 2 to r squared. As you may guess, like that takes t to cosine t and sine t. So it takes pi over 2, okay, not pi over 2, but right here, and we go all the way, right, before 5 pi over 2, we stop. So this is definitely a homeomorphism, right? And it's a homeomorphism between this interval and the unit circle deleting 0, 1, right? Deleting the point at the top. Also, we have any two open intervals are homeomorphic to each other. And we also know that -1, 1 is homeomorphic with R, with some map. And if you're not sure about this, just Google. So by the transitivity of homeomorphism, we see that R is homeomorphic with a unit circle deleting 1 point at the top. So it's basically, if you have a real line, it's a straight line, infinite straight line, you can wrap it up to a circle, right? You can wrap it up to a circle. Yes. So R is homeomorphic with the unit circle deleting the point. It's a unit circle deleting this. But if we include this point, it has 1 point more than this. The unit circle is actually the 1 point compactification of the circle deleting a single point, right? As you can check, right? It has 1 extra point and it's compact because it's closed and bounded, and it's Hausdorff because it's the subspace of R2. And also, okay, we have this homeomorphism here. R is locally compact Hausdorff, right? And it's also not compact. R is not compact, so any 1-point compactification of R is homeomorphic to the unit circle. And this is what I want to say. Any 1-point compactification of R is homeomorphic to the circle. Okay? So that's the end, but it's just some 2 theorems of equivalent characterizations of local compactness that I might not. Okay, I'll just walk through it. Okay, so first, for X's Hausdorff space, it's locally compact if only if it is actually locally compact. What I mean is that for any X and for any neighborhood, there exists neighborhood of V such that the closure is contained in U and the closure of V is compact. Okay, so this is more local compared to our definition at the beginning of this lecture, right? So it's locally compact if only if it's actually some local compactness playing around. This is trivial. Just let C equals to V bar, right? Just let C equal to V bar. It's trivial. And if this direction, okay, let X and X and the area of X, we pick Y, the 1-point compactification, okay? And we take C is equal to Y subtract by U. So C is closed in Y, which is a compact as of Y and X is not in C, which means that, okay, so this lemma is from 1,000 lecture ago, is that for any closed set and a point not in the closed set, we can have disjoint neighborhood of X in the closed set such that, right? I mean, there is a disjoint neighborhood of X in the closed set. Okay. Then we have the closure of Y and V. That's the closure of V and Y is a compact subset of Y. And V bar and W are disjoint. They're disjoint. Okay, so we have this as desired. Okay, so the last thing, given a locally compact Hausdorff space and A is subset of X, if A is closed in X or open in X, then it is locally compact. So given X is locally compact Hausdorff, for any subspace that is either closed or open, it is also locally compact. So it is hereditary. It is, right, in terms of if you're open or closed. And the proof is only like 2 lines, so I'll leave it for you to verify. And that is really it for this lecture. And the most important thing is this theorem. This is the most important thing. And the remarks from here are the definition and the remarks. These 2 are important. And this example is interesting enough, right, for me to write it down. Okay, so this is everything for the 13th lecture, local compactness. And next time, we're finally going to start on separation axioms. And I'll see you guys next time.